of pandemic, doing all the Zoom meetings, something or other goes wrong with the Zoom settings. So thank you for joining us today. Professor, is it Chiara or Chiara?
Yes,
Chiara.
thank you.
Chiara Lo Prete or Prete?
Chiara Lo Prete. Yeah, thank you.
Chiara Lo Prete is an associate professor of energy economics in the John and Willie Leon Family Department of Energy and Mineral Engineering. Her research centers on the economics of energy markets with a focus on the areas of competition and design of electricity markets, the economics of energy infrastructure resilience, and the impacts of environmental regulations on power generation. Recent work has focused on the development of mathematical models and application of empirical methods to study emission leakage, market structures for wind energy integration, resilience of interdependent natural gas and electric power systems, and cross-product manipulation. Thank you for joining us today, and we are really looking forward to your seminar.
Well, thank you very much for inviting me. And first of all, you're able to hear me and to see my slides, right?
Yes.
Awesome. Yeah, so that's great. And thanks again to Anamika, who extended the invitation to speak at your seminar. So part of my research focuses, as we were discussing, on grid resilience and more specifically on the economics of widespread long duration power interruptions. And today's topic is allocating investments to enhance electric grid resilience. And so let me give you a very high level kind of overview of what we're going to talk about today, and then we'll go into the details. So a critical gap in our understanding of how to cope with widespread long duration power disruptions is the optimal mix of preventive measures that reduce vulnerability to these outages versus corrective actions that promote faster recovery when these outages do occur. And from an economic standpoint, investing in a more resilient system has the classic characteristics of a public good with localized and concentrated costs and very difficult to measure benefits. And so electric utilities generally face difficulties in justifying investments that may not yield benefits for years to the regulators. And so this kind of motivates the big challenge that we're facing and the need to do more work to understand this optimal mix of resilience investments. So to try and examine these trade-offs, my PhD student, Ashish Radhakrishnan, and I developed a game theoretic model that represents the interactions between different actors that are involved in making resilience investments in practice. And so what I'll be talking about today is essentially a game among the consumers, a regulated utility, and the regulators that regulate the utility. And again, the goal is to try and get some insights on what should be the optimal mix of these resilience enhancing investments. So first, very briefly, the outline of my talk. I'll give you a little bit of background and motivation. I'll outline the questions, and then I'll go into the modeling approach and the results. I do want to have in the discussion, I will of course summarize, conclude what we've learned from the analysis, but I would also like to give maybe a couple of examples of ideas for work that might benefit from interdisciplinary collaborations between economists and engineers in this space. And just to confirm on the timing, I have until 3 p.m., correct? Your seminar ends at 3.
That's correct.
That's correct. Okay, awesome.
Yeah, we
So
can go a little bit over if there are questions, and if you are available.
No, but I think we should be, I think I should be fine. So let me start. You are, of course, an engineering department, so I probably don't need to spend a lot of time on these definitions because you're all very familiar with them, but just to set the stage. Of course, the North American Electric Reliability Corporation is charged with maintaining system reliability across the US and much of North America. And they have a definition, they define a reliable power system as one, I'm quoting them, one that is able to meet the electricity needs of end-use consumers, even when unexpected equipment failures or other factors reduce the amount of available electricity. NERC divides reliability into two categories, adequacy and security. So in broad terms, adequacy means having sufficient resources to provide customers with a continuous supply of electricity at the proper voltage and frequency virtually all the time. And of course, resources refer to both electricity generation and transmission facilities that produce electricity, as well as demand response programs. Security, on the other hand, is the ability of the bulk power system to withstand sudden unexpected disturbances, such as, short circuit or unanticipated loss of system elements due to natural causes. So that, of course, is different from resilience, which is kind of a less well understood. I think it's fair to say various definitions of resilience exist, but resilience is generally described as the ability to prepare for, respond to, and recover from disruption events, with a focus on these less predictable, high impact, low frequency events that generally lead to wide area outages of long duration. This type of outages represented the focus of a 2017 report by the National Academies of Science that articulates challenges and opportunities related to grid resilience in this space. And so you can see here on the right the cover of this report. And the resilience cycle shown here in the bottom left also comes from the National Academy of Science report. The definition that I'm quoting, on the other hand, is the definition of the Presidential Policy Directive 21, which is a 2013 document, and again, emphasizes these aspects of preparation for, adaptation to, and recovery from these major disruptions. This is another graphic that I'm essentially borrowing from a presentation given by the Department of Energy's Office of Electricity a couple of years ago now. This graphic, okay, just illustrative. Excuse me. I'm not. It's not obtained using any data or anything, but it just wants to convey the fact that with reliability, again, you are trying to. Reliability is driven by this attempt to keep the lights on under a variety of circumstances. But with resilience, you're dealing with the tails of the curve, this curve that relates risk and probability. And so the challenge with resilience is that you're dealing with low probability events. So events for which there is typically little or no empirical data. So unlike reliability, where you have lots of data, for example, to do statistical analysis, the resilience piece is very event dependent. In general, our systems are fairly reliable systems in the United States, but there's, of course, tension around the tails of that distribution. So by understanding the tails, you basically help maintain healthier power systems. So now that we've kind of defined the terms and the difference between reliability and resilience, let me move a little into the specific aspects of how electric utilities may enhance resilience. Actually, before I even say go into that, I do want to emphasize that a lot of measures that enhance reliability, improve resilience as well. And the same entities that are responsible for providing reliability essentially also provide resilience as of now, as of today. But again, my focus here is on the electric utilities. Broadly speaking, most resilience, not all, but most resilience enhancing measures fall into two bins that we're trying to represent here in this figure. You may have preventive or ex ante hardening measures that reduce the vulnerability of the power system to these long duration outages. And examples of that would be, for example, hardening electric power distribution feeders or trimming vegetation near the electric distribution lines. Another type of measures are the corrective or ex post actions. These are actions that promote faster system recovery when the major power outages occur. And again, just to give you an example, if you deploy additional restoration crews or arrange for response equipment to be on standby, those would be examples of corrective measures. There are also, so our study, the study I'll be talking about today, focuses on these preventive and corrective measures. But I do want to acknowledge that there are also not all resilience enhancing measures fall neatly into these two bins. And in fact, there are some ex ante investments that increase the range of corrective actions or lower costs after the disruptions. And an example of that would be advanced metering infrastructure installation to, for example, enable remote detection and faster power restoration. So again, looking at the illustrative graphic, on the x-axis, you have, of course, the amount of time before and after a disruptive event. On the y-axis, you'd have the percentage of electric load that is served in the system. Before the disruption, the utility is serving 100% of the load. In other words, lights are on, the system is functioning well. The disruptive event occurs at time zero, and that's, of course, when you have that a fraction of load served by the utility drops down. So again, for you to remember, preventive measures reduce the vulnerability of the system. Corrective measures enhance the speed at which the system is repaired and recovers its functionality. So after a major disruption, like the ones we're talking about here, state regulators will usually allow most, if not all, of the restoration costs that are incurred by a utility to be recovered from the taxpayers. But the problem is that regulators generally resist funding preventive activities that might reduce costs and outage impacts after a low probability event, because they don't want to raise retail rates to fund investments that may not yield benefits for years in the future. So just to give you some numbers and substantiate this claim, there was a recent national survey conducted by the North Carolina Clean Energy Technology Center. And this was the survey was conducted in 2021 and used data for 2020. And they found that out of approximately $16 billion in grid improvements that were under consideration in 2020, regulators only approved roughly 20%. $3.4 billion. And so this kind of tells you and explains why standard practice for resilience to disasters is fairly reactive, I would say, right, rather than proactive. And what I mean by that is that electric utilities are fairly reluctant to invest in preventive measures because preventive resilience measures, because the benefits of investment may be difficult to measure. They may occur at a very uncertain point in the future, and they may be even allocated to different parties. And so what happens is that utilities today tend to spend very heavily to fix components that failed during a particular event, but do not spend very much in preventive measures. And from an economic standpoint, this is unlikely to yield the most economically efficient mix of resilience enhancing investments, and may not even, by the way, may not capture the range of conditions against which the system needs to be resilient, because you're always fixing elements that have failed in the past events, but you're not kind of, again, taking a proactive approach. On top of that, there is the issue that other actors in general may invest to try and enhance their own resilience. And so now if you move to the right part of the screen, you can see that I'm referring to utility customers. These are basically the end consumers, right? They may also invest to reduce the likelihood of being left without power after an outage. And one way in which they might do so is by purchasing backup generators. Again, an option that does not fall neatly into the preventive and corrective categories that I described before, because the generators need to be purchased beforehand, but fuel costs are only incurred in the event of an outage. So this situation creates a misalignment between the objective of private parties. On the one hand, the utility, and on the other hand, the end customers. And of course, the regulator is a player in all this, right? Because the regulator regulates the utility. This misalignment between the objectives of private parties contributes to basically an inefficient societal mix of resilience investments. And the concern is that going forward, these inefficiencies may even become more serious, because we are anticipating an increasing frequency and intensity of severe storm events that may cause this type of interruptions. Speaking of interruptions, I do want to make the comment, I didn't say it at the beginning, but please interrupt me whenever you have questions. Feel free to jump in, and I'd be happy to take questions during the presentations. Some people don't like that, but I think it's important to have, especially answer clarifying questions if needed. Okay, so with this slide, I'm kind of summarizing the primary research question of this study, which is the one, of course, at the top of the slide. And I'm also listing a few secondary questions. Again, the main goal is to try and get a little bit more insights into the optimal mix of measures that can enhance grid resilience to a particular extreme weather event, which in our case is a severe storm. So how do we go about this? Well, I'll give you an overview of the modeling approach. I don't have the I have like a schematic representation of the model. I've not included all the equations. You can go read all the equations are in the paper, so you can refer to the paper if you want to look at the model formulation. But the key idea here is to develop a game theoretic model, which is essentially cast as a Stackelberg game. So how many of you, it's a little hard, you're kind of small there, but among the students, I guess, how many of you have heard of Stackelberg models before? Is that one student? A couple. Okay. So basically Stackelberg games are games, they're also called leader followers games, right? So in our case, the the leader, the actor, the party that acts first is a regulated utility regulated based on cost of service, and the followers in this game are the utility customers that have varying preferences for reliable power. This preference is expressed by a parameter that is called the VOL, the value of lost load. So the regulated utility acts first. That's why it's the leader. The utility makes investment in one preventive resilience measure and one corrective resilience measure, and the customers decide how much to basically invest in backup generators to reduce the unserved energy during an outage. The graphic here on the bottom left gives you, again, a very, very simple representation of the Stackelberg game and the interactions between the leader and the followers game. Stackelberg games are very closely related to bi-level models, in which the optimization problem of the leader is presented at the upper level. The optimization problem or problems of the followers are given at the lower level, and the upper level problem is essentially constrained by the reaction of the followers. And so considering the upper level problem and replacing the lower level problems by their KKT equilibrium conditions in the constraint set gives you what is called a mathematical program with equilibrium constraints, or MPEC, which is the type of model that effectively we are solving here. So you might wonder why we choose this bi-level approach, and the paper goes into a lot of detail to discuss that. But essentially, a bi-level approach enables you to capture possible distortions in incentives that may lead to these suboptimal decisions in practice. And remember, we're trying to model a non-cooperative framework, right? In which private parties that make resilience investments have conflicting objectives. The utility tries to maximize its own profit. The consumers are trying to maximize the net benefit from power consumption, pretty much. And so you have these conflicting objectives. You have that the good being provided exhibit features of a public good, because, like we said at the beginning, the costs are certain, localized and borne by whoever makes the investments, but the associated benefits are very broadly diffused and uncertain. And so this combination of elements results in inefficiencies that lead to self-interested parties making investment decisions that do not maximize social welfare and the optimal allocation, the optimal mix that we would want. So, of course, the literature has addressed this problem before. There's not a lot of literature on the economics of resilience, but this is an area in which there's been recently some work and research. And so I want to kind of emphasize 3 papers in particular, which are the ones on the second bullet point, that kind of examine trade-offs between preventive and corrective measures using different models, different approaches. What is the contribution that we make? Well, the primary contribution is that all of the models that came before ours, they were adopting, in a way, a social planner optimization approach. So they were imagining that there would be a single benevolent decision maker choosing the mix of individual and system level resilience measures. of course, that's an assumption that doesn't hold if parties have conflicting objectives. And so I would argue that our main contribution is to consider this issue of optimal mixes in a framework that does account for the conflicting objectives of the party through the game theory part of the model. And in addition to that, we are accounting for the distortions introduced by rate of return regulation, which is something that previous studies did not consider. So again, without going, I hope you're able to see this. Can you, yeah, it's a little, can you see it or is it blurred? Seeing. Oh. I think I lost you for a moment.
Yes, yeah, I think now we are back. Can you see us? Yeah, I think it went
cannot. I cannot see you actually. Interesting.
I think the camera is not together. Sorry, that's on.
Yeah, I think, can you hear us?
I can, yeah.
Okay.
I just cannot see you.
Okay, I think you please continue. We are trying to fix the problem because we do have 15 attendees online. So I don't want to disrupt the seminar.
Yeah, now you
Right.
can see us.
Yes, yeah.
But I just wonder because the
Can you see
slides
us
are a
now?
little, yeah, I can see you now. Yeah,
Oh,
perfect.
okay. Yeah,
Thank you. But I wonder if you can actually see the slides.
Right now we are
Yeah,
seeing the MPEG structure.
Yeah, but it seems pretty blurred. I don't know why. It was displaying pretty fine on my end.
Yeah, we have it sharp and clear on our
Oh, you
side.
do? Okay.
Yeah.
So maybe it's just on my end. Perfect. Yeah, as long as it's clear, then
Must be
great.
Teams.
Yeah, it must be because all I see is it's blurred, and so I wasn't sure whether you could see it. But so great. Thanks for confirming. And so again, I don't want to, well, first of all, let me pause and see if there are any clarifying questions on what I said so far. No. All right, so then.
Yeah, we have one question.
Yes, please.
So maybe you can unmute that one. Let me mute here.
I think we might get an echo.
Yeah, I think.
No, if we turn those on, we'll get an echo. Okay.
I think you can hear.
Go ahead. Can you hear?
I can hear you. Yeah.
So maybe you need to come closer. So.
Just wonder, you just said there are some preventive and corrective measures. So how do you define these variables in the model in proportion of investment in preventive and corrective measures, or how do you define the difference?
Yeah, so basically those are decision variables of the utility that is at the upper level, right? It's operating at the upper level. So the utility will decide how many feeders to harden. That's the preventive measure that we consider, and how many restoration crews it wants to deploy. That's the corrective measure. So the amounts will be decided by the utility in its upper level.
Thank you.
Yeah. Yeah, so good
if,
question. And actually, yeah, no, go ahead.
If utility turns off some transmission lines to reduce the risk of wildfire, so that would be considered a preventive measure. Is that correct?
If the utility hardens the lines?
If because what happens is when there is a severe threat of wildfire, especially in our part, they would turn off power to certain transmission lines to
Right,
reduce the risk of wildfire near those lines.
right.
And so that would be considered a preventive measure in this. Is that right? Or is that a corrective measure? Because I couldn't
Actually,
place.
yeah, that's a good question. I would, yeah, that's a good question. And I'd actually have to think about whether I may want to categorize that as a
Okay.
preventive or a corrective measure, because
It is
preventive
reacting.
measures generally in the literature is literally something new that you invest in.
Okay.
And so you make an investment, like again, you harden a feeder or you invest in AMI, right? So you make a new investment with the purpose of reducing vulnerability or enhancing the speed of recovery. In the measure that you just outlined would not really be a new investment by the utility. It would almost be something that they would kind of decide as the situation kind of occurs. And so thank you, and I would like to thank you for making this point, because the challenge that we had was with dealing with lack of data that would allow us to basically consider a variety of measures. So we only could consider one preventive measure and one corrective measure, which were the ones that for which we could find data. But I think, as I will discuss at the end, I think that this kind of studies would really be enhanced by considering more measures, because that would give us much better insights into the optimal mixes of investments, right? If you just consider one investment, one preventive, one corrective measure, yeah, you can get some insights, but they're fairly limited because you only have those two investments. So I think your point is very well taken. Measures like the one that you just told me would be something that could be useful to consider and may be considered in a framework like the one that we have. Yeah.
Thank you. Yeah.
So let me get a little more into again, without showing you the equations, I do want to tell you a little bit about how the model works and how the different pieces of this model come together. I also want to tell you what some of the key inputs of this model are. So you can see that I have like 4 gray boxes that go into the upper level problem. These are fundamentally 4 key inputs into the problem solved by the utility. We need some sort of an assessment of what the probability of a long duration outage would be if no preventive measures are taken. Of course, these probabilities are incredibly difficult to estimate, and that's one of the challenges that we face. But we do need to have some ideas, right, on what those would be. And it's been argued that this kind of probabilities, or a better assessment for these probabilities, may come if utilities run, for example, climate risk and impacts assessments in their own footprint. So again, difficult, challenging to obtain, but you could obtain it and you could test the model for different values of that probability. The second thing that we need are some inputs that go into the problem of the regulator, right? To give you, again, 2 sentences on how regulation works, regulation of electric utilities work. A lot of electric utilities are still regulated under rate of return regulation. And under this kind of regulation, in the US, electricity prices that are charged to the utility customers are set to generate enough revenue to cover utility costs that are approved by the regulator, right? So that's the key part. These costs need to be approved by the regulator. Prices are determined in these rate cases, which are these proceedings that occur every 3 to 4 years. And basically what we need is some idea of the share of preventive expenditures that is generally approved for cost recovery by the regulator, and the number of years over which the recovery of outage damage costs is allowed. These are numbers that, again, may change going forward, but may be informed by the rate cases that the utility has experienced, has gone through until that point. The last piece is the VOL, right? The value of lost load. This is effectively a parameter that reflects the value attached by consumers to uninterrupted electricity supply. So that would be the maximum price that consumers are willing to pay to be supplied with electricity. And at that price, they would be basically indifferent between being supplied and not, sorry, within not, they would be indifferent between paying the price on the one hand and on the other hand not being supplied. So the VOL, there's a lot of discussion in the literature. The VOL is a different number to estimate, and we don't have a lot of data that can inform evaluations of this VOL for low probability events, although some studies have been conducted to try and get estimates of this VOL. How could the utility could still try and get some information about the VOL of its consumers? Typically, this is done using surveys. And so if the utility conducted a survey to ask its customers how much they value reliability, then they could construct a willingness to pay curve for different levels of system reliability, and they could internalize that reliability valuation into their own investment decisions. So given these four numbers that, again, are key parameters, they're uncertain, but can be changed and modified in our model to test sensitivity to different values of these parameters. The utility, that's a leader in our game, it solves the upper level problem. What does the utility do? It chooses how much to invest in preventive resilience, which for us is hardening of distribution feeders. And it also decides how much to invest in the corrective resilience measure. In our case, that's the deployment of restoration crews after the storm. The objective of the utility is to maximize the annual expected profits, subject to basically three sets of constraints. First, the outage probability, the outage damage costs, and the corrective resilience investments are determined as a function of the preventive resilience investments. This is a very important point, and a point that I want to, again, discuss more as we get to the end, because the analysis is critically depends on assumptions on the functional forms for these relations between damage costs and, for example, investments in preventive measures. We make some assumptions on these functions based on past data, but it would be super helpful to repeat the analysis with different data and different functional forms to see how the optimal mixes change as you change the functional forms. So that's the first set of constraints in point A. Point B, the regulatory constraints. The utility essentially accounts for key features of the rate-making process under rate of return regulation. And so that the regulatory process is incorporated in the constraints in part B. And lastly, part C, that's the anticipated behavior of the consumers. Because like I said earlier, in an MPEC, you have that the leader makes its own decisions, correctly anticipating what the decisions of the followers will be. Once again, you may ask, how can the utility know what the reaction might be? It might know that if it has detailed knowledge about the VOL of its customers, and if it can construct, if it has information about the customer load profiles, which would typically be the case if the utility serves its own customers. So that's the upper level. There's a number of variables like the electricity price, the outage probability that are determined in the upper level and are fed into the followers problem. The followers, once again, solve the lower level problem given the utility's hardening decisions and the resulting impact on electricity prices, outage probability, and electricity supply. The goal of the consumers is to maximize their expected annual surplus. And that's done subject to some backup generator output limits and energy balance constraints. We have a number of different customers in the model. And by different customers, I mean customers that have different goals. There are some customers, like for example, commercial customers may have a higher goal, whereas residential customers may have lower goal. And each customer class solves a separate problem. Once you have the KKTs of the lower level problems, you embed them into the upper level problem and you solve the entire problem, which again is an MPEG. How do we parameterize this model? This was one of the hardest part of the model, to be honest with you, because we did not have access to utility data. And so what we had to do is we basically had to choose functional forms and parameters for these functions based on whatever available data is out there. And there's not a ton. The states of Texas and Florida have some data because they are states that have experienced this in the past, especially Florida, I would say. But definitely parameterizing the model was a challenge. And just one last comment with respect to solution methods for those of you who are interested. We could not solve the MPEG using standard solvers like Nitro, and that's because we do have nonlinear constraints in the upper level problem. For example, the outage, the damage cost function, which is the function that relates the damage costs incurred by the utility and the preventive measures, the investment that the utility makes, that's a nonlinear function. And so we can't simply solve the model using Nitro or other solvers, but we had to convert the model into an NLP using something that is called the penalization method, where complementarity constraints are penalized into the objective function. And so we solved the model effectively in GAMS using Canopt 4. So moving on to some of the results. This is a table that comes from the paper, and we simulate a number of different scenarios in which, again, we try to stress test and check robustness of our results to alternate parameters. Remember, some of these we've seen before, phi and rho. So phi was let me just go back really quickly so you can see it. So phi is this one, the share of preventive investments that is approved for recovery by the regulator. Generally fairly low right now in the US. Remember the number that I gave you, roughly 20% is approved for preventive investments is approved for cost recovery. Rho, on the other hand, is the number of years over which outage damage costs are recovered. So if you have a major disaster strike and strikes and the utility has to incur a very, very large cost to cope with this disaster, then the regulator will allow the utility to recover these costs over a certain number of years. And so rho basically represents the number of years over which these cost recovery is allowed. So these are two critical parameters that we want to test. And another thing we consider is essentially the has anybody heard of a performance-based regulation? Again, among the students. So you can see here that there's a column for a penalty for unserved energy. What we're trying to see here is whether it would make sense to introduce utility compensation to customers for extended outages. This is a mechanism that is in place in some parts, in some regions of the US, and some parts of the world. And the idea is that if you introduce a penalty for unserved energy by the utility, then you're effectively making the utility, you're holding the utility like more accountable, and you're giving more incentives to make preventive investments. So the scenarios, the numbers indicate the value of phi, which ranges from 0 to 1. The letters indicate the values of rho, which is, again, the number of years over which outage cost recovery is allowed. And finally, P here, the subscript P, indicates whether the regulated utility is subject to what we call the storm restoration incentive mechanism. And what that means is that the utility will have to pay some sort of compensation to customers in proportion to the amount of unserved energy. So again, let me show you some results for the baseline, which is what is called 1A in the paper. So the first, I'm giving you the results for the MPEC, right, which is the strategic game. You will not perhaps be surprised to see that the model does kind of predict that the utility chooses not to harden any feeder, and so the probability of the 3-day outage, because by the way, I forgot to mention this, but our assumed duration of the outage is 3 days, right? Because remember, we're focusing on long duration outages. So there's an outage with duration 3 days that occurs with a very, very tiny probability in the model, 0.6% probability. So the utility does not invest. The commercial customers, on the other hand, which are the ones who have a very high vol, choose to invest in some backup generation. The residential customers, who are the ones with low vol, they do not invest because their low willingness to pay for being disconnected is not sufficient to justify the investment. And finally, yeah, we have like the damage costs are basically the maximum that you can have if the outage does occur, and the electricity price is higher than if the outage does not occur. Why would that be? Because the damage costs incurred by the utility are passed through the customers. So one of the things that we do in the paper is, of course, you need to benchmark the results of the MPEC, which is, again, an imperfect solution in which you clearly see the distortions in investment decisions. You have to benchmark it with like the socially optimal solution. And so we solve the model from the social planner perspective. This is what we call the SPP. Again, just to put this into context, the MPEC and its customers operate non-cooperatively, right, and without coordination. But in the SPP, the utility acts almost as if it was a benevolent social planner that chooses the mix of individual and system level resilience measures that maximizes economic efficiency. So the objective of the social planner utility is different because in this case, in this problem, the utility is maximizing the net expected social benefits subject to its own constraints and the consumer constraints. So again, not surprisingly, well, I should say that the SPP is of course solved the same using the same parameters of the MPEG. But what happens? Well, in this case, you actually get the efficient mix of investments, right? The mix of investment that would be achieved under perfect coordination between all the different actors in the game. In contrast to the MPEG, the utility hardens the maximum amount of feeders. This reduces the vulnerability of the system to the 3-day outage. You can see this because the probability of the long duration outage is cut in half. As a result, the high volt customers do not invest in additional backup generation, and damage costs are reduced, and the electricity retail rate is reduced. Of course, again, one thing to keep in mind is that if the outage, I'll just say that, if the outage occurs, the damage costs are reduced, but the utility does incur a certain cost for making the investment. So since we're kind of going up to reaching 3 p.m., maybe what I'll do is I'll just jump to this sensitivity, which is the one to the storm duration mechanisms, if that's okay, and then I'll conclude with the additional thoughts on potential collaborations. So electric utilities across the US do not typically offer monetary compensation to their customers for long duration outages. But again, the idea is that if we could tie the utilities' performance to losses that are incurred by the customers, well, that may provide some incentives towards more efficient resilience investments. And this is kind of the idea behind performance-based regulation more generally. So in this sensitivity in the paper, we change the model by considering varying level of customer compensation for long duration outages. And we have like 2 real world incentive mechanisms as benchmark. You can see that one is PG&E, the other one is Ofgem in the UK. Well, Ofgem is the regulator, so I should say the UK. So let me start with PG&E. So PG&E is one of the few electric utilities in the United States that gives some monetary compensation to their customers for electricity outages that last more than 48 hours. And compensation for a 3-day outage ranges from $25 to $50 per customer. And so we basically, given the average hourly residential load in our system, $50 per customer for a 3-day outage would translate into $0.411 per kilowatt hours. And so that's the number that references PG&E. The second benchmark is the incentive mechanism designed and adopted by Ofgem, which again is Great Britain's independent energy regulator. And in that case, the incentive is higher. For a 3-day outage, the compensation scheme would give $465 to each customer. And so converting that into basically, again, keeping into account the average load in our system, we find that the compensation mechanism is about $3.825 per kilowatt hour, which is more than 9 times the compensation offered by PG&E. So we modify the model we have to modify the upper and lower levels to account for this penalty. And we kind of give, in this table, we summarize basically the resilience investment mix for values of the penalties that range from $0 to $5 per kilowatt hour. The level at which we conduct this particular sensitivity is phi equal to 0.25, which again is in line with the share of cost recovery for preventive measures that is close to the national average in the US. What do we see from this table? Well, once again, we're trying to identify ways for shifting the imperfect solution that we get under the MPEG. We want to shift it as close as possible towards the SPP, right? The social planner solution gives us the efficient mix of investments. So what is one way in which we can do that? Well, we can see that a penalty like the one offered by PG&E would already significantly increase preventive resilience investments, right? You can see it because you would move from the baseline in which the penalty is set to 0 to the second row in the table in which already the percentage of feeders jumps to 44% of the total. In addition, if you give a penalty of $3 per kilowatt hour, which is roughly slightly below the compensation given in the UK, that would drive the utility already towards efficient resilience investment decisions. So the insight of this is that since we have regulatory reluctance to approve cost recovery for preventive resilience investments, adopting an incentive mechanism that requires compensation of a minimum amount for a long duration outage can incentivize the utility to invest in preventive measures. And so it would essentially shift the MPEG solution closer and closer to the first best solution. So just to conclude, again, we're studying the trade-offs between preventive and corrective measures to enhance resilience to a particular extreme weather event, which is a severe storm. We modeled this as a leader-follower game, the Stackelberg game, that eventually becomes an MPEG in the way we solve the model. We kind of show that if the utility and the customers act as self-interested parties, the resulting mix of investment is for sure inefficient. And we compare that to the efficient solution that would be achieved in a kind of a social planner framework. Our goal is to move the MPEG solution as close as possible to the SPP solution. And so in the paper, we discuss ways in which that might be achieved. And I gave you an example of the storm restoration compensation mechanism. The last thing I want to tell you, this is my last slide here. I promised I would mention like maybe areas in which this work might be extended, considering possible interdisciplinary collaboration. So the costs of resilience enhancing measures and the functional form assumptions are key elements in our model, right? And obviously are drivers of the results. And a challenge in trying to solve and parameterize these models is once again the lack of data. We considered, like we mentioned, one representative preventive measure and one representative corrective measure, hardening of feeders and deployment of restoration crews. And we chose those measures because costs were available from the literature. That was the primary reason for that. The functional forms and parameters in our analysis were also based on previous studies. You've seen that I insisted a lot on that damage cost function, which is the function that relates disaster damage to the level of preventive investments that are made by the utility before the disaster happens. So now parameterizing that function was challenging because there is very little publicly available data on resource allocation between hardening and recovery activities made by the utilities for specific disruptive events. So we focused, for example, on a logarithmic function in our model because this functional form provided the best fit to the empirical data of another study that was done before ours. The parameters of the log function were derived based on data for Texas. Data availability is a big challenge in this space, and I would argue that better data would enable us to develop models that can provide better insights to the policymakers. So there are some things that could be done to improve the model. One possibility, going back to one of the earlier questions, may be to consider different resilience enhancing measures. I was thinking of AMI because this is kind of a preventive measure, an exemptive measure that enhances flexibility to respond after the event. So it doesn't fall neatly into preventive or corrective, the preventive or corrective bin. And again, parameterizing the functions is super important, and trying to parameterize these functions based on additional real-world data could be helpful to provide more insights into the mix of resilience measures. So if you're interested in talking about this last point in particular, be very happy to chat more. But with that, I will conclude. I will thank, of course, Ashish, who's been wonderful and as in working on the research project. And I also want to thank the National Science Foundation that supports this work.
Thank you very much for the seminar. Now it's the floor is open for questions. The participants online, you can post the questions on the chat box. The ones here, you need to move up to post the question.
Yeah, I had a quick question. If you wouldn't mind going back to your sensitivity slide for a minute. I wanted to ask, this definitely seems to take into account the preventative measures, but maybe I'm reading this wrong, but it looks like the reactive measures, like the effect of increased reactive measures, aren't changing anything. It looks like no matter what, if you look at the penalty per kilowatt hour and the compensation per customer,
Right.
the number of kilowatt hours seems to remain the same regardless of the restoration crews. Maybe I'm misinterpreting this, but wouldn't a 3-day outage with a large number of restoration crews a 3-day outage with a small number of restoration crews, wouldn't that be a shorter outage with a larger number of restoration crews and therefore result in a smaller amount of compensation per customer?
Let's see. I'm not sure I understood your question. The compensation per customer is kind of an input in the model, right? So we are stressing the model with different values of this penalty in the model. And I'm not showing here the kilowatt hours in any of the columns, just to be clear. Yeah, the second column is showing you the compensation per customers in dollars for the entire amount of the outage. And
maybe I can clarify the question. The question is the relationship between the hardening versus the restoration. The idea is if you do more hardening, you would expect to have lesser dependence on the restoration crews, as
Right.
I understand.
Well, it's more so the relation between the first column and the second column seems to be a multiplication of about 122, whereas I would think the number of kilowatt hours unserved would go down per customer as your restoration crew percentage goes up.
Yeah.
No. So this one again is obtained by multiplying this number by the kilowatt hours that are lost during
That's
the
what
event,
he's
right?
asking.
Yeah,
The question
that's
is,
what I'm saying, yeah.
why does that remain constant as the compensation goes up? Because is there a cause and, is there an effect that as you increase the compensation, the utility will take some actions which reduce the number of hours which are unserved? That's the question. So wouldn't the compensation go down? There should be like a closed form relationship between the compensation and the reaction from the utility and how that affects the number of unserved hours. So is that modeled in the formulation?
That feedback is not modeled.
Okay.
That's the, yeah.
Yeah. So there's no feedback loop in that sense. This is kind of maintaining the 3-day outage.
Okay.
Yeah.
Thank you. You had one online question.
Oh, yeah, there is a question online. I will read it. Is resilience treated as a market commodity of some sort where customers pay to minimize the load loss? How is the trade-off analysis justified when customers are getting more compensation in dollar, but utility are paying the most to harden feeders 100% and crew dispatch 63%?
Let me see. Can I see the question somewhere?
Yes, in the chat box, if you click on
Um,
the chat
don't
button on
see.
top.
Oh, there you go. So let's see. I'll start with the first question. Is resilience treated as a market commodity where customers pay to minimize the load loss? No, resilience is not treated as a market commodity. And in fact, I would argue that markets are not very well suited to ensure the provision of resilience, because investing in a resilient system has features of a public good. And we know that markets do not do a very good job at providing public goods, right? Because these are goods that have certain costs, but unclear benefits that are diffused. So no, we're not treating the resilience as a market commodity. And the second question is, how is the trade-off analysis justified when customers are getting more compensation, but utilities are paying the most to harden the feeders? So the trade-off analysis is justified because the customers are, I mean, they are also reducing the amount of backup generation that they invest in, right? Remember, the inefficiency is in the baseline comes from the fact that there's a lot of additional kilowatts that are added to the system, and those come from the commercial customers that have to invest in backup generation because they want to enhance their own resilience, and the utility doesn't do that. So what you're doing here is that you are effectively removing that part of the additional investments, and the utility is indeed worse off because you have that the utility bears more of the cost of the resilience investments. But what you care about is the social, the kind of the economic efficiency in the entire market for the sum of the parties. And so when you add up the efficiency of for all the actors in the game, then you have a higher level of efficiency when a compensation mechanism is in place.
I have a clarification question on the compensation mechanism that say the utility is required to pay compensation to the customers for these extended outages.
Yeah.
Then the utility in turn will go back to the utility commission and ask for some kind of a rate adjustment to pay for this, which will again come back to the consumers or to the customers. So what I'm saying, utility by itself as a business will need to recover that money from the customers one way or the other. Isn't that right? So isn't it that customers are indirectly paying for that compensation?
I don't think it would. No, so the way performance-based, this is kind of an idea. The mechanism we're proposing is essentially aligned with performance-based regulation, right? Which is not you are talking about cost of service or rate-based regulation, in which you, after the fact, you go back to the utility and you try to get compensation for the costs that you incurred. But basically, with performance-based regulation, the idea is that you set a certain target and then you let the utility kind of act, right? if the utility does worse than the target, then it would pay a penalty. But if it does better than the target, then it would actually have some benefit from it. So no, I don't think that the idea is to then go back and get
No,
the
somehow,
money.
as a business, they have to recover their
Right.
cost
So
somewhere,
no.
and yeah.
But the idea is that you in giving them again a penalty for underperforming, essentially, you're giving them a penalty for underperforming. So by giving them a penalty for underperforming, they
They will
now
take it
have a
preventive.
stronger, they
Yeah,
have a
I see.
stronger
Yeah.
incentive to take action beforehand, right? Even though, like your colleague was pointing out, the utility is actually worse off because it actually bears it bears more of the
them.
cost, right? So the utility is not happy about it, but it will invest because otherwise it faces higher negative consequences if it does not invest. Yeah.
Yeah, to stay in business, they have to invest, is what you are saying.
That's correct. Yeah.
Okay. Yeah. I think we lost the screen again. We are trying to reconnect. Yeah, I think we are back. Hopefully you can see us again.
Yeah, I can. Is
Okay.
there a storm right now that is affecting the?
No,
No.
this is all just the
That's affecting
what do we say?
affecting
Yeah,
the
it's
connection.
all to do with the Teams setup.
Okay,
And
I see.
because
I
we
see.
have several industrial members who participate in these seminars, and also from PNNL, we prefer Teams because they are not allowed to connect on Zoom. And we did have some
Oh, I
industry
see.
partners, and they left in the middle of the presentation.
I see.
Yeah.
Okay.
Are
I
there
see.
other questions?
If we have time.
Yeah, please go ahead. Oh, first I should ask you, do you have time for one more question?
Yeah, sure. Absolutely. Yeah.
Yeah, go ahead.
Thank you. Glad that this is
So,
raising
You
questions.
mentioned that there is a certain percentage of the preventive maintenance expenditure that the utility is allowed to recover from the customers. So the question is, how does the regulator determine that percentage? I think you mentioned that it is 20%. So what are the factors that the regulator would use to determine that 20% is going to be recovered from the customer?
So that's a good question, and it varies actually by state. In the US, 20% is a share on a national average. But in fact, if you look at the different states, the share changes a lot. Like, for example, we found that in state like Arkansas, regulators are very, very reluctant to approve major upgrades that would enhance resilience after a disaster. So they very rarely approve preventive measures because they don't want to raise costs for taxpayers in the near term. On the other hand, regulators in Florida are much more likely to allow cost recovery for these preventive resilience measures. So that share, which again is 20% on a national average, is going to be maybe closer to 60, 70% in Florida. You may want to ask why. What is the driver? I think there are some states like Florida, they're definitely more used to these kind of events. And so they probably kind of better grasp the importance of investing in preventive resilience instead of charging everything to corrective measures after the fact. There's also some political decision that goes into that, right? The fact that you don't want to raise the rates for your customers in the near term because that may affect who gets elected next time. That is certainly part of it.
Okay. There is a comment. Yeah, and possibly you can read it on the chat window. Professor Adam Love is
penalty.
He is our colleague in the economics department, and he is an economist, I will warn you.
So let's see. So there should be a penalty that would maximize social welfare. should there be some accounting for the social losses from carbon emissions from proliferation of household emergency generators? So I'll start from the last point. I completely agree with you on this one, and we did give this some thought. We just could not figure out a good way of basically capping these emissions, because the game is between the utility on one hand and the individual customers on the other. So there was no like other mechanism, like a carbon cap or carbon tax to measure the amount of emissions. But we definitely consider that, and I think if not modeling it within the MPEC, we should certainly maybe measure those emissions and report them as one of the metrics, because the emissions would certainly go up as you have many more highly pollutant generators that are built and they emit in those hours. So completely agree on that one. Now, on the point of there should be a penalty that would maximize social welfare, I guess, could you elaborate on that? Like, what do you mean? What do you mean by that? Maybe I can tell you what we did in the model to account for that penalty, and so maybe that will clarify. Or
can you hear me?
Yes, I
go
can.
ahead.
Okay. Yeah, no, it looks like the penalty sort of plays the role of a Pigouvian tax in some ways, right? Because in effect, the regulator doesn't pay for the losses to consumers from power outages, but there is a loss. And so that loss is like when you put the penalty on, it's like charging a tax.
Charging a tax.
Yeah, which would be like a Pigouvian tax in some sense, right? Normally we think about those as externalities. And here there is an externality. But it's internalized by the consumers, not by the principal here, but by the agents. So it was just sort of that analogy seems there, because you're getting like the regulatory outcome as the penalties increases, right?
Right.
And therefore there should be sort of an optimal penalty you could derive that would in effect replace the regulatory environment with more of a Pigouvian tax type idea that's happened in a lot of environmental economics areas.
Okay.
That was just my thought about it. Yeah.
I see. Thank you.
Yeah.
Yeah, just to derive, the optimal level. I see what you're saying. Yeah. Yeah, no, this was done. This was literally, there were some modifications made into the model, into the upper and lower level models to account for the penalty of unserved energy, basically. And then we literally just rerun the model for different exogenous levels of the penalty. So we were not doing what you are suggesting. Yeah.
It's a nice paper. I enjoyed it very much. Thank you.
Thank you.
Yeah, I think probably we should close the seminar. Thank you so much for staying on and answering all of our questions. As you can see, there is a lot of interest. Yeah, there is a lot of interest in this work, and we hope to have future collaborations with you as well. Yeah, thank you so much.
That would be
and
wonderful.
Thanks, everyone.
Thank you. Thank you very much. Bye-bye. Thank you, Anamika.